2 things left. That's it. This package in front of you, this is the end of the chemistry curriculum for me. I don't know if it's you haven't picked up on, but for me, this is the end. I've taught everything after this booklet, okay? Half of it today, half of it Monday, and then we are done. Fingers crossed. You need to practice this more, right? You are going to practice on your own time. Here we go. Titrations. So this is a bit of a review from the titrations of the redox titrations that we did. There's a burette. It contains a titrant. There's an Erlenmeyer flask. It contains the sample and the indicator. Can I tell you how many students do not know the titrant is in the burette? So memorize it now. If they say, when NaOH is titrated with HCl, they need you to know, they want you to know that this means NaOH is the sample, and with HCl means that that's coming from the burette. Okay? So if they ever talk about the thing that is titrated, that's the sample. It kind of is a bit backwards from what you would think of. You would think it's coming out of the burette. No. It's the thing you're looking at. You're looking at the sample. You're looking at what's being titrated. Okay? Does that make sense? So they need you to know that. Sometimes they just tease that out a little bit. And then I've put down here, this should be review. Titration allows you to find out exactly how much, this is from a British book, so alkali as a base, is needed to neutralize the quantity of acid. You start by putting some acid of a known concentration using a pipette, blah, blah, blah. You can read that on your own. Some important words would be end point. That's the point in which the end point is where it ends. That's where you end your titration, where you stop it, where the color change is perfect. Okay, Abby, put your phone away. And stuff in there that you might want to know again about the 0.02 mils, that's centimeters cubed, because that's the same thing as mils. We want all of our results to be within 0.2. And often the first result is way off, because it's just our trial. It's what we just open up the hatchet and let's see, oh, there it changed color. Okay, well, I know it's approximately 20, not 10, not 30. So then I know to slow down at 20 now, as opposed to just trying drop by drop from 10 centimeters cubed. It was 10 mils. Okay? All right, so we often throw away our first one. Remember that? But not always. And we were looking on the final volumes for our 0.2 difference. Okay, so this is the new bit for Chem 30, pH curves. And maybe not though, because we do cover this in Chem 20 from time to time. So pH curves is a graph of how the pH changes during the titration. So if I have started here with a pH that's very low, this is in my sample. So this is like I've got down here, in here, I've got a pH meter. Okay, so in here, I have a pH meter recording my pH. Does that make sense? So I'm recording the sample's pH. So initially, before I've added any drops from my indicator, the pH is very low. So what does that tell you? It must be a strong acid. So that here, this must be a strong acid in my Erlenmeyer flask. Everybody okay with that? I add a couple drops from my burette. And what happens? Nothing, really. Nothing. Add a couple more drops. What happens? Nothing, really. Keep swirling, keep dropping. Still very little change. This is called the buffer zone. Tomorrow, or Monday's lesson, the next lesson, is looking at the buffer zone and what exactly a buffer is. But right now we'll just label it on the graph about the buffer zone. It means it resists change. So you've added 15 mils of base, and the pH is kind of basically the same. So it's buffered. It resists the change. Did you get that? So there's a buffer zone there. This is not a buffer zone, that flat zone. That just means all the acid, well, we'll get there in a second. Okay, so add another drop, add another drop. All of a sudden, within one drop, my volume has changed by half a mil. And all of a sudden, what happens to the pH? Straight up, which is why your indicator color changes, because the pH is drastically changed within that one drop. And that's reached the equivalence point. So that line there being the equivalence point.
So the whole straight line?
The whole straight line. That means, which is also the same as the end point. So the end point was where we ended the titration. What do you think the equivalence point means? What's equal?
When the acid
pH isn't always neutral, that's the problem. Okay, so the equivalence point and the end point. The equivalence point is where you have an equal number of moles. If it's a 1-to-1 mole ratio, as it often is in acid bases, this is your 1 mole is you've added exactly 1 mole. So if I had for every 1 mole in my Erlenmeyer flask, I've added exactly 1 mole from the burette.
So your mole ratio is
The mole ratio is equal. 1-to-1, 1-to-2 sometimes, if it's or 1-to-5, if it's a redox titration, means I have the equivalent number for a perfect, even, balanced reaction.
So if you were to like write out the equation, you have the 5 and the 1, like as the
Coefficients,
right?
yeah.
Coefficients, and that's the equivalence point. Like
Correct.
To get the 5 and the 1.
Correct. Okay? Does that make sense, girls? Does that make sense? Okay? So equivalence point is where the big coefficients are all equal now. And then, what's this point here? What's happening in my flask now? So it's just base, and I keep adding more base. So it gets to be more concentrated, but actually only up to the point of the pH of whatever was in my burette. Okay, so watch this. So here's my flask, here's my burette, right? So right now acid, strong acid, pH 2. Add a bit more, still 2. Add a bit more, still 2. Add a bit more, still 2. All of a sudden I've got exactly the right drop to make it just salt and water, right? A perfect acid-base reaction. There isn't an extra drop of acid, there's an extra drop of water. All of it has become acid all of the acid's been reacted, and it's just salt and water. Everybody okay with that? That's this point here. Then I keep adding my base, because I keep the volume going. I keep adding the base, keep adding the base. What is now going into my salt and water? Salt. More base, adding your base. More base is going in. So as that base goes in, it reaches the pH of whatever that base was in my burette. So what must my pH of my burette have been? 14. So what was in my burette? A strong base. Did you get that? Emily?
Will it always be an acid in the
No.
flask?
No.
It can like switch.
Yeah.
So if you were titrating the base with an acid, the graph would look the same, just it would start at the top
Backwards.
and go down.
Right. So if we were to switch these guys and we were to have the base be in our flask, the pH meter would say it started at 14, that strong base. And there'd be a buffer zone, buffer zone, buffer zone, equivalence point. And then you just keep adding acid, acid, acid until it's reaching its, sorry, that should be a bit more, not, a bit more dramatic there. Oh. Until just my acid being added. So here's my pH of 2 now. Okay? Yes?
So at the end of that one, you would have technically twice as much base as you did acid to begin with, because when you had the equivalent amounts, it would be the equivalence point, or like the pH 7.
Yeah?
Like when you had equal amounts. That's
Not
what it
necessarily
would be.
pH 7. Look. It's not necessarily pH 7. At that equivalence point. So you can't say pH 7, you can't say neutral, you say
But
the
like
moles react. I mean the moles are the same.
Okay.
Okay? and not necessarily double. Just depends on how long I go for. If I stop here, then not double. Okay. So here, a strong acid, you see, I'm starting with strong acid. Yes? And then when I end with just my base from the burette falling in there, I only have a pH of 9-ish. So that's a weak alkali. Get it? And the equivalence point of this, let's say HCl and ammonium hydroxide, it's a weak base, or sodium carbonate will be a weak base. What's the equivalence point pH here? 4. Yeah. So those of you that thought you reached a neutral solution, that's not necessarily true. If you have a strong acid, strong alkali, you've probably reached a neutral solution. But if you have a weak base and a strong acid, you're going to end up with a pH of 4 at your equivalence point.
Can you actually put a number on your equivalence point?
You know.
No.
No, but they might put a number.
Okay.
So what is the pH at this equivalence point of this graph? Question 1 would say 1, or A is 1, B is 9, C is 4, and D is 7.
So as long as it's somewhere along the straight part.
Right, so 7, do you see how that's not really on the straight part? It's on the cusp of the, and they put 7 in there to throw out people that think neutral always for titrations. Okay?
So sorry, what's the top flat line?
The top flat line is where I have my salt and water, or whatever it is, my products, and I've added excess. What have I added excess of at this point?
Base.
Excess base here. Excess base.
Is there a name for it? Just excess?
Just excess base. And here, actually, in my overall solution, what do I have?
Excess acid.
Excess acid. Okay, so here's a weak acid, because you can see I started at a pH of 5. Do you notice this little lip here? This little like hump before you begin the buffer zone? Okay, that exists in your weak acid. And then we end at a strong alkali pH. And here the equivalence point falls around pH of 9-ish.
What is that little?
Pardon me? That little hump? Just what happens.
Doesn't matter?
No, because it takes a second, because this is an equilibrium. So it takes a second for the equilibrium to adjust before it reaches a buffer zone. So that's just an initial influx of base. And here, this weak acid, weak alkali, do you see how you've got this smooth curve? There is no real sharp end point. You see that, Devin? Devin? No sharp end point. You awake?
Yeah.
Good. Okay. So no sharp end point. So for this, we don't tend to use an indicator, we tend to use a pH meter because it's so wonky, you kind of want to make sure you're getting the right pH. All right?
Junior class change.
Happy days? Okay. And you might have used the pH meters and done these curves in Chem 20. I didn't do it last year for those of you that were in Chem 20 with me last semester, but I did it this semester. Okay, so using the graphs on the last page, label a buffer region that's different from the one that I labeled for you. Label an endpoint, an equivalence point, the titrant area that has excess acid, area that has excess base. So a quick little activity for you right there. Or if you want, if yours is a bit messy with notes, you could create another graph, like just draw a graph and label everything on that one graph. That's fine too. Okay? So you've got 2 minutes to do that. Just another tiny little bit left on titration curves. The titration curve of a polyprotic acid or base. What's polyprotic mean?
More than one protons.
Protons, right? So an example, can you put that away please now, Evan? An example of a polyprotic acid?
H2CO3.
H2SO4. Another one?
H2CO3.
H2CO3. Yeah. Another one?
Carboxylic acid.
H2SO3.
Na2CO3 would be a polyprotic base. Good. Okay, so whenever you have these polyprotic acids or bases, you have 2 lumps on your titration curves. because you transferred, or well, pardon me, for something like H2SO4, 2 protons will be transferred. The H2SO4 will go to HSO4 minus, and then that'll go again to SO42 minus. So for each proton that's transferred, you end up with 1 extra hump. Okay, you remember that? Remember doing polyprotic bases and transferring 1 proton at a time in your reactions? Okay, so this is just the graph of it. So for example, here I have a polyprotic base. So we've started at a basic pH. So there's your basic pH there. And at point A, I've reached some kind of an equivalence point there. And it's that, for that reaction. So here's the CO3 2- accepting 1 proton and getting HCO3- and water, just 1 proton. And then at point B, I'm taking that product and adding in the second proton to get your final full compound. Does that make sense? Okay, so then another example then is, I've done another example for base. Oh, I also wanted to point out that it's even weaker. It's even in a weaker base, so therefore it's lower pH. Okay, so here you've got your H3PO3 titrated against your sodium hydroxide. So strong-ish and strong-ish. So because this is basically strong, I've started at a basically strong pH. Because this is basically, no, because that is strong, I've started at a strong Raj. I've ended at a high pH. And because I have 3 protons to donate, I have, only 2 equivalence points, but that's because when you get to the last one, hold on a minute, ba-da-da, ba-da-da, yeah, the last one, it's so, the water falls so much uphill that you don't actually get a hump for it. Okay? Do you know what I mean? So it lies so much to the left. The reactants are favored so much that you don't actually get an equivalence point because you can't get it to react to get the products. So in all intents and purposes, it's easier to think of it as it's non-spontaneous and therefore it doesn't happen the third level. Okay? Choosing an, I forgot, we're taking this a little bit on there as well. Choosing indicators. So, have you used a variety of indicators throughout your titrations? Yeah, sometimes phenolphthalein, sometimes methyl orange, sometimes bromothymol blue. Depending on which 2 you're reacting, according to those graphs that we just spent a lot of time looking at, your equivalence point is different. Different pHs. And different indicators are better for different pHs. Okay, so when you're choosing an indicator, you have a look at the graph and you go, I don't like this bit there, I don't like this bit here, but this zone there is where I can choose an indicator to change color. And if it changes color of that indicator, happy days. So this is a bit of blurb about how indicators work. Basically, if they're an excess acid, they're one color. If they're an excess base, they're in another color. So 2 different colors depending on if it's an acid or a base, because it itself exists in an equilibrium. So different indicators have different excess standards and thus change color at different pHs. So in your data booklet on page 10, you'll see a whole list of a lot of indicators with a lot of different pHs. So have a look at your data booklet, page 10.
And it's saying on that graph, is like the indicator range.
Yes.
It's just like you have to indicate.
I'll show you an example. Okay? So here's the titration curve for this reaction. Choose an indicator that changes, that you would use to find equivalence point A. Choose an indicator that you would use to find equivalence point A. Lindsay, do you even have a data booklet out? No. Well, can you get it out, please? Looking at page 10.
Thymolphthalein.
So you're looking for something not around 12, not even around 11, but something that falls between 10 and, I don't know, 7.8 or something like that. One of the ranges that's in there. And you think, what?
Thymal,
Or phenolphthalein.
Is that phenolphthalein or thymolphthalein?
That one's thymal.
Okay, both work.
Yeah.
Okay, quite often you'll end up with 2 or 3 that work. But of course, there'll only be one in the multiple choice selections out of those 2 or 3, okay? So let me see if I agree with you. Thymolphthalein is a 9.7 to 10.6. Yes, I'm all right with that? Oh yeah, I did.
It says 7, but you wrote 4.
That's my dyslexia coming out in like full force. Right there, proper evidence. There you go. Never listen to what I say. Oh, that's why I can't say colors either sometimes. Okay, and what about if we were trying to choose an indicator for B? What would we choose?
Bromocresol green.
Bromocresol green. Let me have a look at bromocresol green.
Or methyl orange.
Bromocresol green is 3.8 to 5.4. Yeah, that works. And
Orange. Methyl orange.
methyl orange is 3.2 to 4.4. Which do you think would be better? It's hard to tell on this graph, but anyway, it is hard to tell because you can't quite see whether that's 3.5 or 3.2, right? But I'm thinking 3.8 looks like it's more in that zone. Okay, do you understand how to choose indicators for their colors? Did you note that the indicator color is there? So let's say we chose methyl orange for this example. Okay, we chose methyl orange to be our indicator for B. Craig, is that your phone that you're playing with or something else? Okay, good. So that's, what color would it change in our solution?
Methyl orange.
For methyl orange.
Red to yellow.
Are you sure it's red to yellow, not yellow to red?
Why?
Okay, why? What pH do we start at?
Because it says it has pH increases on the thing, and
Yes.
we have pH decreases.
Right, well, look, you've got to look at the graph. So is your pH high going to low?
Yes.
Ah, so we're going from base to acid, so we're going from yellow to red. Do you see that?
Yeah.
Okay. And you also have Kas for all these acids as well. And the Ka for this would just be, so methyl orange is HMO, which of course plus water goes to H3O plus and MO minus. You see how that's MO for methyl orange, by the way, not like a compound, not a symbol. Methyl orange, because it's a big long thing. It doesn't really, you don't really care. Okay, so MO for I don't really care. So that's da-da, and then the Ka for that would still be, you know, x squared over HMO. And the Ka is in your data book, the value. So you could find the pH in which this changes color. Does that make sense?
Yeah.
And the pH in which it changes color better fall in that range for your calculations here. See how they're related, and see how they could ask you a variety of questions. But that's no different than the work we did this morning, or I mean, first thing class. And just a note on the other side, colors of aqueous solutions. If you need to find a color, how would this reaction, you know, what would you see in this reaction color change? It's there. If they give you a crazy one, you know, that you don't really know, you should know copper sulfate's blue, no problem. But you might not know what nickel sulfate would be colored. Okay. So you can look it up there. I don't even know if it was in there.
Yeah.
Yeah. Okay. Okay. So that's it for today, and you've got 15 minutes to start on your homework, which will be these titration questions here. And it's only question 1 and 2, but some of you will need to finish the questions from yesterday. Yes? Craig?
Yep.
Jacob, are you okay? You with us, Jacob?